Hello everyone, good evening. So this is going to be for the notes from the professor over fermentation part 2. So this is going to be like the fermentation systems, the gas exchange scale, and the processes involved. Again, part 1 was over some other topics like the batches, different types of growth, and just different conditions like the pH, the temperature, nitrogen sources, as well as carbon sources. This one is going to be about the systems itself and the gas exchange and all those different components. So let's get back to where, there it is. All right, so the first thing, the fermenter designs, or designing the fermenter systems, we need a maximum reliability, we need minimal cost, and these are going to be more expensive than chem reactors due to the considerations that you need to make for microbes. You're growing microbes in these. So reactors can be classified as internal mechanical agitation reactors. That's the first type here. Then we also have external circulation. And then our third type is bubble column. Those are the just 3 types of reactors. All right, let's look at the stirred bioreactor. This is going to be the most versatile as well as the most common. They're going to be lab scale from 500 ml to 20 liters right here. Production level, it's going to be 3,000 liters. So we have these components of it. So we have baffles, which will increase the turbulence at the wall. We have the stirrers, which are going to be creating this sensation, this stirring motion from bottom or top to agitate and facilitate the gas and nutrient exchange. So it's going to be stirred from bottom to top in order to, cycle through all those nutrients and cycle the gas in the system. A jacket will also be provided to control temperature, and a sparger will be supplying O2. Types of stirrers, we have 4 types. The disc stirrer is the most common. This is going to be where we just have blades projecting out, usually 8 blades beyond the disc diameter, so kind of like just a common fan thing looking type thing. A turbine type stirrer, these are going to be curved blades. You're going to have a required 50% less air for the same yield. So there's 50% less air. You don't have to pump as much for the same amount of yield with a turbine. We also have the MIG stirrer, MIG. This is going to be the multi-stage pulse counter current stirrer. The maintenance of sterility. So how to have a sterile system. So we need to decrease the amount of openings. We need to add double seals on the agitator shaft. We need to have welded joints. We have the slant sterile pipes to allow condensation to drain. We don't want it to get stuck in a pipe that's just directly left to right. No, we need a slanted one so it slides away all this condensation. And the ports need to be steam sterilizable. The bubble column reactor is where you have air or gas introduced through the sparger at the bottom of the fermenter, and then the flow rate of gas or air influences the exchange of oxygen as well as the agitation. All right, now let's look at the airlift bioreactor. So the applications would be for aerobic fermentations. We have high efficiency. It's also used in wastewater treatment as well as in the single cell protein production. That's going to be your airlift. Let's talk about disposable systems, also known as wave bioreactors. You're going to have a ready-to-use system, no sterilization. You don't need cleaning validation either. You just have short delivery times as well as low initial investment costs because you're just getting this this reusable bag. However, there is a scale limit, so you're limited to a 500-liter scaled bag. It's difficult to run complex processes such as perfusion. So principles again of the wave bioreactor, you have this like platform on this thing that's going to rock back and forth. So air comes into the bag. Let's draw that. Air comes into the bag, and then you're going to have a wave motion. So this is going to rock back and forth. And then as that wave motion happens, you have the cell culture and the media kind of getting agitated here. And this is going to move the oxygen around. And then you have your exhaust, the exhaust air coming out at the other end. Let's talk about single-use bioreactors, also known as subs. This is similar to a stirred tank, which we covered at the beginning, but it has this disposable bag in it. It's stirred by the impeller. It has pH dissolved oxygen as well as temperature control. And it also has a sparger to provide aeration. There isn't any sterilization here, and you could get up to 2,000 liters in this type of bag in the single-use bioreactor. Okay, let's talk about gas exchange and mass transfer. It looks like stirring. Okay. Let's talk about gas exchange and mass transfer. So we're going to have some equations here. So I'm actually going to just write all of those out again. So gas exchange and mass transfer. So you need this gas exchange. You need really good gas exchange for large-scale fermentation according to the notes. Oxygen is the most important gaseous substrate. And carbon dioxide, you don't want that. That's the most important metabolic product, but you don't want a buildup of that. You need to remove CO2, and you need to have a lot of oxygen because it's the most important gaseous substrate. Oxygen is going to be a limiting factor since oxygen solubility is really low. It's about this number here, 9 milligrams per liter at 20 degrees Celsius in water. When you add the ingredients in the medium, however, this will lower the solubility of water even more, of oxygen. Sorry about that. So if you add medium ingredients, this will lower the solubility of oxygen in water even further. That's why oxygen is a limiting factor. Right, so the solubility of gas could be described by Henry's law. So this is going to be describing the solubility of oxygen in a nutrient solution in relation to partial pressure in the gas phase. So spooky chemistry is back again. Okay, I'm going to just erase this and write out the equation again. So Henry's law is C arterisk equals PO over H. C arterisk is the oxygen saturation concentration. Sorry if I sound like I have a cold. That's because my right nostril, for whatever reason, is clogged. I don't know what's going on. Anyways, this variable here, PO, that is the partial pressure of gas in the gas phase. So PO is divided by H, and H is Henry's constant. So again, Henry's law will look at the solubility of oxygen in the nutrient solution in relation to partial pressure, and this has to be in the gas phase. Let's look at the mass transfer of oxygen. Here we go, another equation. Okay, so The mass transfer of oxygen is characterized by another equation. This is Na is equal to Kl times A times C arterisk minus Cl. That's in parentheses. C arterisk minus Cl. That's in parentheses. And that's going to equal the OTR, also known as the oxygen transfer rate, in millimolar O2 divided by liter times H. Okay, so again, I think I'm just going to rewrite this so I could actually go through all the variables. I made a mess here with writing this because we were going really fast through the notes, a tiny bit faster than I was anticipating, but we could rewrite it. Okay, so the mass transfer of oxygen can be categorized by Na is equal to Kl times little a times, in parentheses, C arterisk minus Cl. And that's going to equal the OTR. The OTR is also known as the oxygen transfer rate. And the units are millimolar O2 per liter times H. Alright, so let's go through the variables. So Na, that's going to be the volume dependent mass transfer. Okay, and that's going to be basically the same units here, millimolar O2 divided by L times H. Kl, this is Kl times A, sorry about that, Kl times A. This is volumetric oxygen transfer coefficient. Kl, now going individually to this is the transfer coefficient. At the boundary phase. And then A is going to be the specific exchange rate, or the specific exchange surface available for diffusion. And then for diffusion. And C arterisk, this is a different C arterisk. This is going to be the saturation value of the dissolved gas in the boundary phase. And then Cl is going to be the concentration of the dissolved gas. The units are big M, so millimolar over liter. Alright, so mass transfer of oxygen will be the Na equals Kl times A times, in parentheses, C arterisk minus Cl, which is going to be the OTR, or that whole equation is going to equal the OTR, also known as the oxygen transfer rate, in millimolar O2 divided by L times H. That is a mouthful. The variables, again, are there. Na is volume dependent mass transfer. Kl is the transfer coefficient at boundary. A is the specific exchange surface for diffusion. C arterisk is saturation value of dissolved gas at boundary. Cl is concentration of dissolved gas. And Kl times A as a unit here, Kl times A, that's volumetric oxygen transfer coefficient. Versus Henry's law, which is, again, Henry's law isn't showing mass transfer. Solubility of gases is shown by Henry's law, which was the C arterisk, which is the O2 saturation concentration when we're talking about Henry's law. is equal to the partial pressure of gas in gas phase over Henry's constant. That's Henry's law. And then also remember the C asterisk, it's different in the mass transfer of oxygen equation too. Oxygen transfer just means from the gas bubble and then into the gas liquid interface, and then that's now mixed in the liquid, and then the liquid cell interface, now that gas or the oxygen is going inside the cell from the liquid into the cell. That's what it's basically talking about. All right, the critical oxygen concentration. So the gas absorption rate. I didn't see this written down anywhere. There we go. I had it up here. Okay, so the gas absorption rate is not constant during a fermentation because at the end of fermentation, when a substrate other than oxygen is limiting, then the gas absorption will be reduced. So again, that same point is put here in the notes I took during the lecture, because there will be a time where the substrate runs out. When the substrate other than oxygen is limiting, then the gas absorption will be reduced. So you have to look at the critical oxygen concentration, or C-crit. So I'm going to actually just change this. Critical oxygen concentration. And the critical oxygen concentration is used to indicate the value of the specific oxygen absorption rate. So there's two things here. The critical O2 concentration is used to calculate the specific O2 absorption rate. So when the oxygen absorption rate is lower than the critical concentration respiration rate. Okay, let me see. The respiration rate is correlated with oxygen concentration, the solution. When the absorption rate is higher than the critical concentration, then there is no dependence of the respiration rate and the dissolved oxygen. There's no dependence in this situation when the absorbance rate is higher than the critical concentration respiration rate. And that means that it doesn't matter how much oxygen is present in that situation. So let me erase this and we'll try to go over that again, because even in lecture I was really confused about it. I'm going to just erase it and we're going to try and figure out. So when the oxygen absorption rate, so the OAR, oxygen absorption rate, is lower than the C-crit, or the critical O2 oxygen concentration, this means the respiration rate is correlated with oxygen concentration in the solution. However, when the OAR, the oxygen absorption rate, is greater than the critical concentration of oxygen, this will mean that there's no dependence between the respiration rate and O2 present. An example of this would be, I guess, let's see, E. coli has a very low K-crit. However, something like Pseudomonas has a very high K-crit. Those are just critical oxygen concentrations of some organisms from a little chart on lecture. Gonna just highlight some of this. So when OAR is greater than K-crit, no dependence between respiration rate and O2 present. Okay, that's why I have look up next to that thing. All right, Now, where am I? Okay. Now we're going to determine the oxygen uptake rate. So there's a dynamic method. That's method number 1 in determining O2 uptake. So the dynamic method is when the rate is determined by measuring the decrease in dissolved oxygen after aeration has been turned off. So basically, you turn off the addition or the supply of oxygen in the system, and then you just measure the decrease in the dissolving oxygen. This is going to look like a slope. Our second method, again, involves a lot of chemistry. So chemistry, just hold in there. I personally don't like how complicated this thing is. Okay, so sulfite oxidation method. So we're using the sulfite oxidative method. In the presence of 10 to the negative 3 m copper 2 or CO, I don't know what that is. CO, is it cobalt? Copper and cobalt ions, sodium sulfite. So sodium sulfite will oxidize to sodium sulfate by the dissolved oxygen. The dissolved oxygen will turn sulfite into sulfate when there's copper or cobalt. I'm guessing that's cobalt. Could be wrong, CO. The reaction takes place very quickly, so the oxygen concentration in the solution is 0 since it's so quick. Okay, so now you could find how much sulfite became sulfate by titration. On the slide, it says in samples, the remaining sulfite can be determined. So you're looking how much sulfite is left. So in samples, the remaining sulfite can be determined by adding the aliquot to an excess iodine solution, then titration the iodine with sodium thiosulfate. So let's write that. So first, you add iodine to the sulfite or potential sulfite that hasn't been oxidized to sulfate, and then you are going to titrate the iodine and with sodium thiosulfate. Okay. Basically, measure how much sulfite hasn't been changed into sulfate, ATE, and then that's another way to determine the oxygen uptake. All right, let's talk about scaling up. Scale up is the conversion of laboratory procedure to the industrial side. So lab conditions, again, don't equal industrial scale. So lab scale is based on the optimization based on yield. It's based on yield. So biomass per ml of broth, that's going to be for single cell protein. However, max yield per unit of time is going to be for penicillin. Industrial scale is the maximum yield for minimal operating costs. So max yield for minimal costs and time. We have two important methods. The constant power consumption over unit of broth, which is below right here, and the constant volumetric oxygen transfer rate. So let's look at the constant power consumption per unit of broth. So when we're scaling up, let's see what this constant power consumption versus unit over unit of broth. Okay, so the energy input will be matched in scaling up. So we're going to match that energy input. An example would be when novobiasins titers are plotted against energy input for 3 impeller types. This will show that with the same energy input, novobiasin production is dependent only on the impeller. So we don't need to add more energy. We're going to have this thing here like that. This is what the graph looks like on the screen in Canvas. So we got to this kind of like area where kind of like leveling out, right? So now novobiasin is up here, the novobiasin production. Once we get to this area that the energy requirement, it's going to be the same for, however, growth. Now, this novobiosin production, it's based off of whatever type of propeller. That's the only factor once we get to the constant power consumption per volume. All right, let's talk about not the permafrost. Why did I say permafrost? The fermentation process now. So let's talk about growth of the inoculum. So we're going to have to revive the culture by shaking in a liquid medium or in a solid medium. From frozen, we're going to be looking at bacteria. That's going to be 4 to 48 hours. And then fungi, we're going to have it like 1 to 7 days. To obtain enough inoculum for small fermenters, you're going to need a second round with more flasks or larger flasks too. So you need to make sure you have enough inoculum for the fermenter. All right, let's talk about the fermenter free. Not the fermenter. Why am I saying all these weird words? Fermenter pre-culture. So this is the pre-culture. We're going to need it so there's enough inoculum for a larger fermenter. Again, scaling up, we're going to an industrial level. So we have the optimum inoculation level for the production fermenter. Bacteria, the optimum amount of inoculation would be 0.1 to 3%, whereas fungi and actinomyces will be 5 to 10%. Okay, so that in mind, the amount of inoculum required determines the number of pre-culture stages. There'll be a delay in the production if there's too little inoculum, so you need to follow this. 0.1 to 3% for bacteria, and for fungi and the actinomyces, you need 5 to 10%. Okay, so let's say we have this starting thing, 1 liter of fungi at 10% inoculum as the optimum. So how do we scale up to get that 10%? So we could take our 1 liter from here. We're going to take all of that broth and we're going to move it to a 10 liter. Since 10% of 10 liters is 1 liter, we could put that into a 10 liter thing. And then this other 9 liters will be from like broth. And then, so what if we want to do another 10%? Okay, so what is 10 liters 10% of? It's going to be 100. So we're going to have 10 liters of the previous solution and then 90 liters in addition of the broth. I'm almost finished. Okay, sorry about that. We just have a few more things to look at. Let's look at the fermentation parameters, the production fermentation parameters. So temperature, most will be run at the mesophilic range of 20 to 45 degrees Celsius, or the thermophilic range, which is about 45 degrees and up. So I'm going to add a plus at the end. We need a high temperature for growth and then a drop in the temperature for production. Again, because the growth temperature doesn't always equal the product temperature. Control is critical. A 1 degree Celsius above the optimum temperature might be 20% lower yield in penicillin acylase. So 1 degree change in the optimum temperature produces 20% lower yield of this penicillin acylase. So that's how important the control of that is. Right, so product fermentation parameters, more of them. Aeration. So aeration, it's usually 0.25 to 1 ppm, or volume per liquid volume per minute, and you adjust. Pressure, to avoid contamination, overpressure is used to control any contamination. You're going to be using 0.2 to 0.5. Pressure also influences the solubility of CO2 and O2, so you need to worry about that as well. Again, O2 is good, CO2 is, we don't want that to build up. Stirring, so the impeller speed will depend on the size of the fermenter. So we're going to need a variable speed drive. All right, that's going to be all of the fermenter notes. There's a ton in part 2, but yeah, that's all of it, all the ones that were marked for the test. All right, thanks so much for tuning in. Please do something nice for someone, and take care.